Okay, so we're very happy to have Jan Steinebrunner, and he will speak about the one-dimensional bordism category.
Yeah, thanks for inviting me to speak here. Would of course have been great to come in person, but that's a bit tricky at the moment. Maybe another time. Yeah, so I'm going to talk about the one-dimensional bordism category today. And what I try to do just generally during the talk is going to just mark the things of the screen that I'm talking about so that you know where I'm looking at. And can I send maybe I should send the PDF to this chat. Let me, how do I do that? One sec. It's a great start of the recording. Oh, I can't pull things into chat. That's odd. Okay, apparently I can't share files. Well, then I just do stop me if I ever go too slow, and I'll just go back and you can look what I was writing. All right, so let me start properly. Yeah, so I'm going to talk about the one-dimensional bordism category. And when I say one-dimensional bordism category, then I do mean that the morphisms themselves are one-dimensional. So this is really the bordism category in that dimension where you think that really nothing exciting happens. It's all intervals and circles. You just glue them together and you get more intervals and circles. But yeah, I guess my job today is kind of to try to convince you that there are some quite interesting things that turn up when you look at this thing closely. And everything I'm saying is going to be based on this paper. I'm not going to talk about some aspects of it, but yeah, I have some selection of it. All right, so let's get started. And I just want to start by, well, maybe repeating something you all already know, but just to fix notation. So what are these bordism categories? Well, for any dimension, the bordism category corp D is going to have as objects the closed-oriented D-1 manifolds, M, N, and so on. And then a morphism from one closed-oriented D-1 manifold to another is going to be a diffeomorphism class W of compact-oriented D manifolds whose boundary is identified with M and N. And now there's a few things to be careful about. So, well, here's already a picture. So I want to make sure that I identify diffeomorphic bordisms, but I only identify them if they're diffeomorphic relative to the boundary. So I have to respect this identification. And also, everything is going to be oriented, but I'm probably going to sweep that under the carpet for most of the time. But so the incoming boundary should have the reverse orientation. But yeah, we'll see when that ever comes into play. All right, and then composition is just defined by gluing. Again, there's some details, but maybe the best way to see this is to just look at pictures. And the pictures I drew are in the two-dimensional case. So this is the surface category, COP2. And then what I do is I have this morphism from two circles to one circle, it's just a pair of pans. And I have an endomorphism of the circle given by the two-puncture torus. And I can, well, glue those together like this. It doesn't really matter which representatives I chose of the diffeomorphism class. And then the important thing to note, I guess, is that in this definition, I really just identify diffeomorphic bordisms. So this thing represents the same morphism as that thing. I can just put the genus one here, or I can put it up there. All of these are just on the nose identified. Yeah, and this bordism category has been around for a while. The earliest reference I know is Milner's lecture notes from the 60s on the ethical bordism theorem. And I guess he uses it there because he wants to wants to talk about H cobordisms. He wants to decompose bordisms and just keep track of how they glue together. And I guess that's what this thing does in general. It knows about D-manifolds with boundary, and it knows about how these D-manifolds with boundary can be glued together. All right. Now there's another version of the bordism category that has played a very important role in some algebraic topology of manifolds recently, and that's this topologically enriched bordism category. This one's a bit more tricky to define, so I'm just going to sketch it. But the idea is roughly as follows. So this thing has as objects closed-oriented D-1 manifolds again, except that now they're going to be submanifolds of some fixed infinite dimensional R infinity. And somehow the idea is that this R infinity is big enough so you can embed whatever you want, and it doesn't really matter how you embed it. But this is good for concreteness sake, because now if we have two such submanifolds, you can just say that a morphism is really a submanifold of R infinity cross an interval. And this interval is of some length t. That's what we call the length of the bordism. And then we require that the boundary of W is exactly m cross 0 and n cross t. So I have a picture that maybe makes that clearer. Here we have the bordism of length t. R infinity is just drawn two-dimensionally due to lack of space, but m's embedded in here and n's embedded in here. And now W is not just some abstract diffeomorphism class, it's just on the nose a subset of this big space that satisfies the property of being a submanifold. Again, technical details, it should probably be cylindrical around the boundary. All right, so this is now just a very concrete set of these subsets, and this can be topologized using the Whitney-C infinitive topology. So the idea there is that I want to be able, in the space of bordisms, I want to be able to do smooth deformations. And so in particular, if you give me any two diffeomorphic bordisms, W0, W1, between the same manifolds, then, well, previously I just identified them on the nose, but now, because R infinity is sufficiently big, I can always find an isotopy between these two embeddings of essentially of the same manifold. And this will lead to a path that connects these two as points in the space of submanifolds. And somehow a derived version of that is also true, namely that loops in the space correspond to self-diffeomorphisms. So diffeomorphic things are identified, loops correspond to self-diffeomorphisms. And well, the homotopical way of saying that is that this the space of bordisms from M to N is constructed exactly such that connected components are these diffeomorphism classes. And then every connected component is equivalent to the classifying space of the diffeomorphism group of that bordism relative to the boundary, everything oriented. So this is like, I might call this the moduli space of that bordism. And somehow there's a lot of like very specific choices, and it's a bit like when you talk about the loop space and it's not strictly associative, and then you do more loops instead, and that's strictly associative. So that's a bit the kind of like you're not changing anything homotopically, but you need to make some concrete choices to get an actual category out of this. That's topologically enriched. Okay, so this is somehow a fancy version of that COP-D. I'm calling this CD because that's how it's called in parts of the literature. Yeah, notation kind of varies. If there's confusion about which one is which, just let me know. And so I just have a comparison of these two things that we've seen so far. So on one side, we have this COP-D, and on the other side, I now wrote BORD-D, which is a bit ironic because it's not like one of them are co-bordisms, the other one are bordisms. But again, this is standard notation. And the idea is that this topologically enriched category, you can also, if you want, think of as an infinity one category. It's just, well, it's a category enriched in topological spaces, and have we can construct an infinity one category. And this thing is has a lot of higher structure. All these higher morphisms encode the diffeomorphisms of the bordism, and it's modeled by the CD. And on the other hand, the COP-D, we can recover that as the homotopy category. So taking the homotopy category of some topologically enriched category would exactly involve taking connected components, so collapsing this to a point. Right, and that's what we do. Here, diffeomorphic borders are identified, whereas here we just keep track of the size structure. And then maybe something I'm actually not really going to talk about is that also both of these things turn up when you think about topological field theories. And COPD is kind of the thing that's been around for a long time, and it's good enough to formulate what TQFTs are in the sense of a tier. But maybe BORD-D I guess even a fully extended version of that is somehow what turns up in Lurie's proof sketch of the bordism hypothesis. And so this is it's like the free symmetric model category on a dualizable object if everything was framed and so on. So this is somehow has some nice properties from this infinity categorical perspective, but certainly COPD is the easier object. All right, I should make a warning that I sometimes call this COPD the discrete bordism category because it's a discrete category, it's just an ordinary category. But I shouldn't do that because there's some really interesting work by Sam on discrete bordism categories, and they are called discrete bordism categories because they are discrete diffeomorphism groups. And this just happens to be a bordism category and discrete. So I'm calling it either the truncated bordism category or it's the homotopy category of the bordism category. All right, so those are the two bordism categories that turn up and what I'm going to talk about. And now the perspective through which I want to look at these is that of classifying spaces. And there are some pretty good reasons to look at classifying spaces, at bordism categories through classifying spaces. And one of those is the work of Pilates, Matzen, Tim, and Weiss. So what they did is, just realized, maybe I'm not sure how clear it is what a classifying space is. Let me just say it's a construction where you that takes categories to spaces, and I'm calling it B. And the point is kind of if you look at groups in here, for example, then this sends G to BG, where BG is the thing, you know. So it's taking the nerve and then realize. And these classifying spaces of bordism categories, well, for this topologically enriched one, they were computed by Pilates, Matzen, Tim, and Weiss, and the result is that they're equivalent to loops infinity minus 1 MTSOD. And I always think telling this to someone who doesn't know it, it's a bit of a weird theorem. You take something with 2 letters and express it in terms of something with 5 letters. But it is actually a good theorem because the thing with 5 letters on the right-hand side, this is just some kind of Tom spectrum that's very amenable to just techniques from algebraic topology. So in a sense, on this side, you can just compute anything you might ever want to compute. Maybe for concreteness, if you look at the surface category again that I drew earlier, then in this case, MTSO2 is also known as CP infinity minus 1. And that's just it's almost the same thing as the suspension spectrum of CP infinity but with an additional cell in degree minus 2. So if, say, we want to compute the cohomology of that, then we know the cohomology of CP infinity. There's all the powers of the first Chern class. And then from that, it follows that the cohomology of this guy, of the surface category, essentially, it's a polynomial ring on kappa 1 to kappa 3 on these kappa classes. Okay, now I started all of this out by saying this is a useful perspective. So I should say why it is. And well, one way of viewing this is that somehow the bordism category contains all of these moduli spaces, B diff of the bordism, for all bordisms at the same time. And so therefore, somehow the cohomology of the bordism category is like the cohomology of the diffeomorphism groups, but all at the same time. And this is true in a more mathematical sense, namely that if you look at surface categories, for example, and gamma G1 is the mapping class group of a surface of genus G with one boundary component, then the cohomology of this mapping class group is in a range given by Hara stability or improvement self, in a certain range where the cohomological degree is low. The cohomology of this mapping class group is isomorphic to the cohomology of the surface category. So in this sense, the surface category really is the limit of the mapping class groups cohomologically as the genus becomes larger. And together, these two results would imply the Mumford conjecture, which was, however, proven by slightly different methods earlier by Matzen and Weiss. So this is not the first proof of the Mumford conjecture, but somehow this is motivating to compute this classifying space as the limit of all of these moduli spaces. And then, of course, these cohomology classes that you have on the classifying space here, well, they pull back to cohomology classes on the mapping class group. And there they are characteristic classes for bundles of surfaces. All right. And then more recently, somehow this same strategy has been used by Galatius and Randall Williams. And they don't just do it in dimension 2, they use this result in higher even dimensions and manage to prove a similar, if you want, convergence result there, and deduce a lot of things about diffeomorphism groups of even dimensional manifolds of dimensions at least 6. So, right, so in this sense, all of these moduli spaces together give a very nice category, and we can compute the total classifying space and then deduce back things about the moduli spaces themselves. All right, so this is all about the topological image category. And the question that I want to ask or talk about today is, but what about this easier category? What about the classifying space of the homotopy category, of the bordism category? And I mean, this whole thing somehow, I guess, started out as a curiosity, because I was thinking, well, COP-D is pretty much like CD, except that we don't have these complicated moduli spaces in there. And in principle, that should make things easier. So it's just an ordinary category. It's not topologically enriched. And I thought, well, then I should be able to compute the classifying space. But it turns out that it's somehow not that easy, because at least you can't use the same methods as for this topologically enriched category, because there all of your manifolds, all of your bordisms were embedded in some big space, and you could use these geometric techniques, or more specifically, you could use Siegel's method of scanning, where you kind of look around a neighborhood of every point in R infinity. And so this doesn't work anymore. And it's not entirely clear how you would even approach computing such a classifying space. Okay, so let me just recall what we already know about these classifying spaces of COP-D. And I guess, well, what I didn't write down is COP0. So COP0, what's that? Well, objects are -1 manifolds. By convention, that's the empty manifold. And then morphisms are oriented 0 manifolds. And that's just finite sets with an orientation, but only up to diffeomorphism. So I only need to remember how many positive points there are and how many negative points. So really, morphism in here is just given by 2 natural numbers. This is just a fancy way of writing the product of 2 natural numbers. And therefore, the classifying space is going to be the product of 2 circles. So not very exciting. Okay, but in higher dimensions, one thing that was known is a result by Ulrike, and she was looking at the surface category. I'm always scared that the indexing is confusing, so let me scroll back. So all of the pictures I drew are in the COP2 case. All of these are in the surface category. And she showed that the classifying space there can be split as a product of S1 and some X, where X is a simply connected infinite loop space. And I guess for the perspective of what she was trying to do to compute invertible TQFTs in dimension 2, that's enough, because somehow you only need essentially the first cohomology group. which is given by this, and somehow the TQFT that is seen by this computation is this Euler characteristic TQFT that sends a surface to half its Euler characteristic. But really, maybe with this in mind, and also seeing as there aren't that many things in COP2, one might think that X is maybe contractible, or at least not very interesting. So this is, in a sense, a negative result to bounce what can happen. And similarly, there's this other result, this theorem by Johannes Ebert, that, well, is totally not meant to be a result about COP-D, but you can think of it as one. And what he showed is that, well, we have this computation of the topologically enriched bordism categories, and whenever you have some closed 2D manifold, so this only works in even, well, there's a version in odd dimensions, but let's say in even dimensions, whenever you have a closed manifold, then you can think of this closed manifold as a bordism from the empty set to the empty set. And the moduli space of this manifold, so B diff of W, therefore lives in the classifying space of the bordism category. And so there's a canonical map. And what he showed is that this is injective on rational cohomology. So it means that any of these, if they're higher dimensional generalizations, can be detected non-trivially on one of these manifolds. But now what I'm doing, if I look at COP-D, is that, well, the map from the topologically enriched bordism category to COP-D is going to mod out all of these moduli spaces. They all collapse to a point because they're diffeomorphic bordisms. And so the composite from here to there and then down to COP-D is a trivial map. And since this one was injective in cohomology, we know that this comparison map between CD and COP-D just has to be trivial in rational cohomology. So that would mean that we can't lift any of the kappa classes, any of the interesting cohomology classes we already know from here to the homotopy category. However, we will see some kind of kappa classes on here, but maybe we'll talk about that more later. And we already know that they will definitely descend to zero. So there's something else going on. All right, so this was kind of two more negative results in that not that much can happen. And so here's a positive result, and that's from this paper that I mentioned earlier. And the idea, well, what this result says is it completely computes at least the case in dimension 1. So the classifying space of COP1 is equivalent to an infinite loop space, twice delooped, of the fiber of a map of spectra from empty set to HZ. And the map is the generator in cohomology. So somehow, morally, the HZ here doesn't really matter. It doesn't change that much. Yeah.
What do we know about the rational cohomology of the loop of B COP-D or COP2D? Do we know any non-trivial class there?
So of this guy, oops, of B COP-D? No. So I think everything I wrote above is like all that's known. There's no way really. Somehow what you could, I think my first guess would have been to lift a kappa class, but somehow what this corollary is saying is that, or extend, I don't know, is that none of these classes can be detected, and you don't really have any methods to detect any non-trivial cohomology class.
But so you're also saying that anything there is going to map trivially to the loop of B Curly C2D. Although
yeah. So I'm saying this could be mostly zero. I don't know anything about that, but I know that the composite map going from here to there, this composite map is trivial. And I know that this first map was injective in cohomology, so the second one has to be zero.
I see.
Okay,
thank you.
yeah, somehow this is like a negative result that tells you that at least these kappa classes that we already know in CD won't help us get anything non-trivial or detect anything non-trivial in COP2D. And I think it's a very, like, somehow, if I think at the time that Ulrike did this, it was a very, I don't think she said that anywhere, but it would have been a very reasonable guess to just say, for example, X is contractible. There's just no higher cohomology whatsoever. And maybe B of COP-D should be boring in general. And somehow what we see in this like very low dimensional case already is that because of this MTSO2 here, the cohomology of COP1 just turns out to be some big polynomial ring, uncountably many generators in degrees 2i plus 2. So let me just write that down in degrees. So it starts in degree 4, 6, 8. So there's a lot going on, and it's, I mean, just from the way I stated the theorem, it's not really clear where all of that comes from. Yeah, and somehow in the COP2 case, I have some conjecture, and this is, I'm trying to write this up at the moment. Somehow the COP2 case itself is not super interesting. It might actually be that the X here is fairly small and not that interesting. But somehow you can make a very small change, which is, you notice by COP2, chi less equal 0. So what I mean by that is that I only allow bordisms that have connected components with non-positive Euler characteristic. I mean, there aren't that many surfaces. The only thing it means is I don't allow 2 disks and 2 spheres as bordisms, and I don't allow them as building blocks. But there's still all the cylinders and all the higher genus surfaces. So if you look at this very large subcategory, then what I think happens is, so this is just rationally for now, what I think happens is that you have the circle again, but then you get some big free infinite loop space on a double suspension on a bunch of interesting spaces. They correspond to the different genuses. So this is genus 1 is gives you a BO2, and then genus 2 gives you, and higher gives you these tropical moduli spaces that a priori have nothing to do with COP2. And they are known to have a lot of non-trivial cohomology, so it grows exponentially. There's like work by Galatius, Chan, and Payne who show that this cohomologically contains the Grothendieck Teichmüller Lie algebra. So it's, yeah, there's just a lot of things going on here, and it's very much not this trivial category that one might think. But yeah, I have some notes on this in the very end if I end up having the time. Ah, right. And before I get to, I actually want to spend some decent amount of time just talking about why this theorem is true. But before I get to that, just one more question along these lines that I just find very curious, which is that what is the classifying space of the category of finite sets and cospans between them? So there's this very simple idea that if you have any kind of category that has, I don't know, finite colimits, then you can build a category of cospans where the objects are the same, so they're finite sets. And a morphism is just going to be a morphism from A to B is just going to be a cospan like this. And then you compose cospans by push, oops. You compose cospans by taking pushouts. And this is just a very simple categorical construction. At this point, I should also remark that oftentimes when you look at your favorite category and you ask what is this classifying space, the answer is oftentimes just it's trivial. And the reason for that is that if a category has an initial object, then you can contract everything onto there. If a category has disjoint unions, then you can also define a contraction. There's just a lot of these algebraic categories just have a contractible classifying space. But a lot of these very geometric categories where objects are, in some sense, morphisms are geometric objects in a sense, and composition is somehow by gluing. In a lot of these examples, it's just very unclear the classifying space would be. All right, so I mean, for now, this is just very, very curious that there's so much cohomology turning up and there's this big spectrum. So I want to go a bit into why any of this would turn up at all. All right, so this is now the proof sketch of that theorem. And the way it goes is, well, we already know from Galatzis, Matsutim, and Weiss that in this topologically enriched category, there we know what the classifying space is, and it's MTSO1, which with a shift that cancels out and so on. So what it turns out to be is just the free infinite loop space on a point. This isn't terribly exciting, and it's also cohomologically essentially like the identity component is rationally trivial. So, but we know what this is, and we kind of want to start from there. And now what we need to do is we need to compute the difference between the topologically enriched category and the Somatopic category. And there always is a functor from a topologically enriched category to a Somatopic category, where what you do is the objects just go to themselves, and on morphisms, I take this embedded bordism W with a length T, and I just send it to its diffeomorphism class. Such a functor always exists, but in general, the classifying spaces on both sides don't have anything to do with each other. And we're kind of lucky that in this case they do. All right, and we also know on morphism spaces what happens. Well, this is the disjoint union of all of these moduli spaces, but any point in this moduli spaces represents the same diffeomorphism type of bordism. So all of these just get collapsed to a point. Okay, and we're in dimension 1. So the manifolds that do turn up aren't that complicated. There are 2 building blocks, of course, for one manifolds. There's the interval and the circle. And for the interval, the diffeomorphism group that fixes the boundary is contractible, just because there's many reasons. You can just write down a linear homotopy, or you could say the Alexander trick works in dimension 1, and you can just maybe just write down the linear homotopy. So this group, while as a discrete group, it's probably very interesting. As a topological group, it's just contractible. On the side of the circle, I can do a bit more. A subgroup of the diffeomorphism group of the circle is the rotations, SO2, and somehow homotopically, that's all you can do. So the moduli space here is BSO2, so CP infinity. And now what I want to do is to study these 2 configurations separately. Because in general, as I said, there's no formula relating topologically enriched category and Somatopic category in terms of classifying spaces. Okay, so I just decompose all bordisms, and the way I do that works in any dimension. Is I call a bordism closed if it's a closed manifold. So if its boundary is empty, that means M and N were already empty manifolds, and W is just a closed manifold. And some other complement is I call it reduced if none of the components of W are closed. And this is just defined in such a way that if you give me any bordism like this, then I can always decompose it into a closed part and into the reduced part. And I can put them back together, and then they give me back my bordism W. So it's this very canonical decomposition. And we kind of want that on the level of categories. So we just go ahead and define the closed bordism category. And we define this as the full subcategory of CD on the object empty set. So this has one object, and the morphisms are just the closed D manifolds, and the composition is by a disjoint union, essentially. And this is easy to define because it's just a full subcategory. Okay, now on the other side, it's a bit more tricky. So this reduced bordism category, CD reduced, well, this should now have the same objects as CD, but I want only those morphisms that are reduced bordisms. So I don't want any of these closed components. And there's a problem with that because that's, can I scroll? Yep. That's not a subcategory. right? If you look at these two bordisms, this is a reduced bordism, there are no closed components, and this is a reduced bordism, and then I glue them together, then I get this guy, but this one has a closed component. So I can't define it as a subcategory, but rather it's going to be a quotient category. And what I need to do is that if I compose, then I first glue and then delete all closed components. Just do the same thing as you did before for gluing, and now you delete these closed components. All right. So this is category. That's I guess you have to check that this is associative, this composition, and well defined. But that gives you a topologically enriched category, and somehow by construction they fit into a sequence of symmetric monoidal topological functors. So you have this closed category. That's a subcategory of the entire topologically enriched category. And then we have the reduced category, and there's a functor down here that sends any bordism to its reduced part. And if you have another look at how we defined composition down here, then you see that it's exactly such that this quotienting operation that discards the closed components is functorial. Okay, so in a sense, this should be the decomposition of our bordism category into its closed components and into its reduced components. Now, well, on the level of bordisms, it's always a product decomposition. You can always say it's the datum of a bordism is just the same thing as a datum of a reduced one and a closed one. This isn't true on the level of categories. So the middle category is not the product category of the two. And the reason is somewhat exactly these circles that turn up here. So the functor R doesn't have a functorial section. There's no consistent way of choosing preimages. Maybe the better way of thinking about this would be as some kind of central extension. All right, but what is true is somehow the next best thing, which is that after taking classifying spaces, the middle thing isn't the product, but it fits into a fiber sequence. So this gives you a fiber sequence of infinite loop spaces. That's how it's stated in the paper. By now, I think somehow a better way of proving this is actually to say that these categories, well, they're symmetric monoidal, and I can think of them as infinity one categories, and as such, as symmetric monoidal infinity one categories, this is a co-fiber sequence. So what that means is that if you take the CD and you take the quotient by the closed full subcategory on the empty object by this closed subcategory, then the quotient as symmetric monoidal infinity categories is the reduced bordism category. Which is, I guess, visually makes a lot of sense, because take all bordisms and you mod out the closed ones, then you get the reduced ones. And yeah, so you can prove that, and then it's somehow a consequence that this is a fiber sequence of infinite loop spaces. But that's really all we're going to need. That somehow this, I guess, doesn't decompose as a product, but somehow as a twisted product, i.e. as a fiber, as a total space of a fibration. All right, and the same holds for the homotopy categories here. Again, somehow this is not a formal consequence, because these things have nothing to do with each other in general. It's just, it holds by the same reasoning, the same arguments apply. All right. Okay, now I have this fiber sequence. I have this decomposition into circles and intervals. And how do I use that to actually compute something? Well, we already know the classifying space of the one-dimensional bordism category. It's free infinite loop space on a point. And we can also easily compute the classifying spaces of the closed components, because these categories here, they just have one object. They're by definition the full subcategory and the empty thing. So they're really just monoids. And if you think about what this is, a morphism in here is the diffeomorphism class of closed one manifolds. But every closed one manifold is just a union of circles, and all you need to remember is how many circles there are. So this is really just another way of writing the natural numbers, and then the classifying space is S1. Up here, it's a bit more tricky, but it's also completely classical. Somehow this is freely generated by the moduli space of one circle, which is equivalent to BSO2, and therefore you get this free infinite loop space here. All right, right. And now we're kind of good to go because, well, I guess we're good to go if we know what this map is, but luckily this was worked out in work of Gelasius. When I said that with him in the audience, he looked very confused. So maybe I shouldn't be citing his paper. But there also is a paper by Gian Siracusa that states this explicitly and also in more generality. And so the point is kind of, you can just work out what that map is. For those of you who are familiar with transfers, this is an instance of the transfer with respect to a circle action, I guess with respect to a trivial circle action on a point of the stable transfer. And then once you know what that map is, you realize that this is actually the map that fits into the Genauer sequence, which is another sequence that turns up in this context of bordism categories. And you know that the fiber is going to be loops infinity -1 empty SO2. And then because it's a fiber sequence, you can continue as one to the right. Everything is loopable, and you get the result here. So somehow that's how we work out the classifying space of the reduced bordism category in the topological image case, just by knowing the other terms. And now we're almost done because on this reduced side, we have that all the moduli spaces that turn up are just bdiff of a bunch of intervals. And we already said that if the bdiff of an interval relative to the boundary is going to be contractible. So these moduli spaces that we had in the reduced bordism category are just, they don't contribute anything homotopically. And therefore, this thing is already actually equivalent to its homotopy category. And we also have empty SO2 here. And this is already kind of the theorem, because now you know that the thing we want to compute is a fiber bundle, a circle bundle over this space. And if you think a bit more about it, you can work out which circle bundle it is and also write it as the homotopy fiber of a map here, BS1. I think I did that below. Right, yeah. So as a consequence of this, you really get this just this computation of bcop1 as an infinite loop space here as the homotopy fiber of this map. And then by standard arguments, you can also just compute the rational cohomology if you like. And it's all of these kappa classes. Well, I'm calling them kappa classes because they also come from empty SO2. But it's important to note that they're actually in a different degree. So as I said before, they start in degree 4, 6, 8, so on. All right. Yeah, let me just put that into context and then briefly wait and see if there's any questions about this theorem. Yeah. So what I mean by put it into context is just say a few things that are also true that I maybe already know. And some of what we used is that in the topologically enriched case, we have the free infinite loop space on a point, which in a sense is much smaller than what we get out there. So for example, the rational cohomology there is trivial. I'm always just looking at one connected component, by the way. So there it's trivial, but here we have all of the kappa classes. So somehow in the homotopy category, a lot more is going on in terms of cohomology. And then another thing you can compute, if you like, is also pi naught and pi 1 of these things are just known. I guess pi naught of the bordism category is just the 0th cobordism group, which is Z. And then finally, the other thing that's maybe worth noting in this that we came across in this process is we also computed the classifying space of this reduced category, be it of the homotopy category or the whole thing, they're equivalent. And there we got out the empty SO2. And this empty SO2 is related to the computation that by Galazza, Smith, and Tillman Weiss, who showed that this actually turns up in the classifying space of the surface category. And the one thing I want to point out there is that there is a shift because we kind of did this de-looping of the fiber sequence by 1. And so this reduced bordism category looks a lot like the surface category, but there's just a dimensional shift one level down. And this is also somehow maybe one of the reasons to actually call these things kappa classes, because over here they're definitely kappa classes. They're millimeter monthly classes. All right, I think I've been already saying a lot of things, so maybe I'll just briefly wait if there are any questions about that.
Quick question. How should you think of these kappa I bars as a characteristic classes?
Yeah, so I don't, yeah, I think they're via this odd equivalence, they're related to things that are definitely characteristic classes, right? Because here I can, like if I put a loop, I can map into it from B gamma 1. Oops. But somehow on the one-dimensional bordism category, it's not clear why these would be characteristic classes. So I don't think that there's a type of bundle where whenever you have such a bundle, you get a map into the classifying space of COP1.
Is there a map from loop of B COP1 reduced or unreduced to BC2? I mean, they are homotopy equivalent, but is there a map?
So there is somehow a zigzag of functors that I think induces this map, but it's a bit odd. If you, instead of C2, you look at the board 0, 1, 2. So this is an infinity 2 category where I kind of I start out with points, then I do my monomorphisms are one-dimensional bordism, my two morphisms are surfaces with corners. Then this has the same classifying space, but once looped. And now in here, there is a subcategory where you only allow very few two morphisms. You only allow somehow disks and intervals, and that then projects down to COP1 reduced. So there's this weird zigzag, but I'm like, for example, translating. So I'll say more about how we can understand what these kappa I really are, but somehow the first thing I tried in understanding these was trying to think about what they are here and then get them through the zigzag, but that doesn't really doesn't seem to work somehow.
All right, thanks.
So yeah, I don't think there's like a good comparison map in that sense. Right. Yeah, but I want to say something far more concrete about these kappa I and maybe how to get at them. And before I do that, let me just make some very philosophical remarks about why we should have expected this result and not expected this thing to be trivial. And what I think is that COP1 having a lot of cohomology and the classifying space being fairly big should tell us that it is in a sense not freely generated as a symmetric monoidal infinity category. Or somehow you need a lot of generators to generate it as a symmetric monoidal infinity categories. And if you know the cobordism hypothesis just in dimension 1, then that tells you that if you take finite sets and bijections, that's the free symmetric monoidal category on one object, and right, this has all the symmetric groups in there. And then what you do is you add duals. Then this adding duals and classifying spaces should correspond to group completing. So you're group completing all the symmetric groups, and well, what you get out is that's why you get out QS0. That's the result that we saw earlier. So this makes sense. So that thing is freely generated by a dualizable object and therefore fairly small, but it automatically, even though you didn't put it in as any generator, it automatically comes with this BSO2. It comes with a circle, and the circle has these symmetries. And you get that for free. And now if you want to look at COP1, what you need to do is you need to remove the BSO2 by hand. And in doing so, you need to add a lot of generators, right? Because this is CP infinity, it has cells in all even degrees. And that's what these kappa I bar kind of do. They kill off this BSO2 that would be there in board 1 or in C1. Yeah, so that is why I think it makes sense that this thing is somehow big, because the more natural object is maybe board 1, where you would have the BSO2. Okay, but maybe a far more down-to-earth way of getting at these kappa I and understanding what's going on is to somehow look at this equivalence that we have, that somehow and extract concrete map from it. So from BCOP1, actually, let me go to the next page. We had these fiber sequences. Maybe just draw them in. There was another fiber sequence here. And now what we can do is we start out at BCOP1. We go to the reduced category. That one was equivalent to the topologically enriched one. So you can go up here, inverting that equivalence. And then we can continue this fiber sequence and deloop that space once to the right. And we get some free infinite loop space on the double suspension of BSO2. And so this zigzag should give us a map from BCOP1 to this big free infinite loop space. And actually, if you forget this additional base point, then that you can check this is rational equivalence. So this sees all of the cohomology classes. And somehow on here, we have the Chern classes. And then on the big thing, we have the kappa I, and they should pull back to these kappa I that I have here. And if we understand this map really well and we find a concrete model for it, we have a shot at maybe saying what these kappa I really are. Okay, and so there is a construction that does that. You can just explicitly write down a map of simplicial sets that gives you this map. And I just want to roughly sketch how this goes, because I think it shows a lot about how this thing relates to BSO2. All right. So to do that, I'm going to draw a lot of pictures, or show you a lot of pictures. And what we need to draw a lot is this nerve of the bordism category, the one-dimensional bordism category, which is just a simplicial set. And what I drew here is an element of N4, N3 of the bordism category. So this is a 3 simplex in the nerve of the bordism category, right? So you should ignore these vertical lines. They're just there to tell you where bordism starts and stops. But really, this is one bordism here, W1, oops, W1, W2, and W3. They're 3 composable bordisms. I just drew them next to each other so that the face map is exactly given by forgetting one of these bars. All right, so this is a way of just writing down that thing. And now what I do here is I define a simplicial set cut n. This is a space of cuts. And it's cut n is a subset of this nerve where I just require that M0 and Mn are empty. And I also require that all of the intermediate bordisms are reduced. So an example would be this thing here, where kind of I'm not allowed to touch this line, I'm not allowed to touch this line, and I'm not allowed to have circles that just fly around without without being cut. So that's a thing you can define. It's not a simplicial subspace. It's a bit like this reduced bordism category. It's not a subspace, but it's rather a quotient. So there's this quotient map that just looks at some simplex and it just throws away everything that violates the condition that I wrote down. So we only remember this guy and this guy. All the other bits are disregarded. And the simplicial structure on here is just defined so that this is a simplicial map. So for example, if I imply D2, that would mean I delete this line, then that's fine, that doesn't do anything. If I apply D3, then that means I delete this line. But somehow then, if you just imagine this thing gone, and this part of the bordism gone, then these things now touch the final M. They touch the boundary, and the boundary is supposed to be empty. So I have to delete these. Hope this makes least some kind of sense. But yeah, you can define the simplicial set and just define the phase maps appropriately. And then, of course, by construction, there is a map from the nerf of the bordism category to the simplicial set of cuts. It's just defined as a quotient. And now the theorem that I also proved in that paper is that, first of all, this space of cuts is actually this free infinite loop space on the double suspension of BSO2. So we'll see more about that in a second. Firstly, this is this free infinite loop space, and secondly, the quotient map is actually the desired map. So it's this zigzag of maps that we wanted to construct a model for. And if we properly understand why this thing is equivalent to this free infinite loop space, then somehow we could understand the kappa classes on here, on the space of cuts, and then we can just pull them back via this just simplicial map. All right, so what does this space of cuts have to do with BSO2, with the rotation group, or with S1, I guess? Well, so the first thing, and I'll kind of gloss over that, is it will be enough to just consider connected cuts. So we don't have to look at components where there's multiple circles here. We just have to look at those diagrams where the entire thing gives you one circle. And the reason for that is that the rest will somehow be freely generated as an infinity algebra by the connected bits. So this is an example of connected cut, and it's a 3 simplex. Yeah, maybe you just leave that for a second and we just consider the connected cuts. This corresponds to this free infinite loop space symbol that we saw there. So if you look at connected cuts, then the next thing that you notice is that in here, if I apply D0, deleting this bordism, well, then definitely something is going to touch this line, and therefore it's going to get all deleted. So that means that somehow D0 and Dn will always go to the base point. And that's because this first and this last phase aren't really very interesting. And it turns out that somehow you can forget those, or you can think of them as being formally added to a previous simplicial set. And what this means, and this is also a bit tricky, but what this means is that the space of connected cuts is the simplicial double suspension of some other simplicial set, which I already presumed here as the nerf of some category. Okay, let's also just believe that for a second. I just want to get to the point of where we get to SO2 or to CP infinity. Okay, if you believe that, then what are the objects of this mysterious category F that I call the factorizations of S1? Well, this should be connected to simplices in cut. And such a connected to simplex is, well, it starts out with an empty set. You have an empty set at the end, and then you have one zero manifold in the middle and 2 bordisms. And these 2 bordisms are required to glue to a circle. And now I claim that, in a sense, this is the same data as that of a cyclically ordered set. How do you extract that? Well, these things are oriented. I'm just going to mark the positively oriented points. So there's 3 positively oriented points, and these 3 points, they live on the circle. So I have an induced cyclic ordering. So a set of 3 elements here is cyclically ordered. Okay. And then for what are the morphisms in there? So I should look at cut 3. So note that there's shift by 2 because I have this double suspension. Okay. So this, I'm just marking all the positively oriented points again. Here. This point, I follow the circle until I hit that point. From this point, I follow the circle until I follow the circle in this direction until I hit that point, and here until I hit that point. Right, so just writing it down very briefly, somehow the map that you get is this. And it's, from what I've told you, it's absolutely not clear that any of this is actually well-defined or gives you a category or whatsoever. But I hope you can see at least a bit that there are cyclic sets turning up in this, and somehow the nerve of the category of cyclic sets turns up in some way. And then you can actually show that this mysterious space of cuts that we had earlier, which was really just constructed from the one-dimensional bordism category, this space of cuts is the free infinity algebra on the double suspension of the nerve of this cyclic category lambda that you might or might not know from, I don't know, cyclic homology and that kind of things. Okay, and I realize that my time's over now, so I'll say 2 more sentences. First of all, other people have thought about this. Iguza, for example, has constructed cocycles on this cyclic category that represent the Chern classes, because the classifying space of the cyclic category is CP infinity or BSO2. And then you have all of the C1 to the N in there. And Iguza has constructed explicit combinatorial cocycles for these. And since I have this map to cut, I can just pull them back to COP1. And then you get cocycles like this. And this is just a picture of the lowest one, of the kappa one, where you input a 4 simplex, and it produces for you a rational number, right? That's what a 4 cocycle is. It goes from here. It goes from here to rational numbers. And the way it does it is it kind of just looks for these, circles that aren't really there in the bordism category, but they're written as composites of bordisms. And then it somehow does some Evering procedure with cyclic orderings that I can say more about if you like. But there's some like super combinatorial formula that you can just write down, and it somehow sees this kappa class. And yeah, maybe I'll stop here.
Okay, so let's thank Jan for his talk. Are there any questions? Maybe I'll stop the recording and ask for questions again.